looked at a reaction type that can take place in water, and that was a precipitation reaction. In today's class, we're going to look at two other types of reactions that can take place in water. The first is a neutralization reaction involving an acid and a base, and the other is a oxidation reduction reaction, also called a redox reaction. Common skills across all three of these reaction types include predicting the products for the reaction, writing the balanced equation, and then writing the net ionic equation. Starting with the acid-base neutralization reaction. Here we see hydrochloric acid reacting with sodium hydroxide to produce water and sodium chloride. Hydrochloric acid is the acid, sodium hydroxide is the base. The product of the reaction includes water and then the remaining cation and anion. That's what forms the salt. In this example here, hydrochloric acid is a strong electrolyte. Sodium hydroxide is also a strong electrolyte. Water, molecular non-electrolyte. And then finally, the ionic compound sodium chloride is also a strong electrolyte. If we're going to write the net ionic equation, the plan, we first want to begin with a balanced equation, dissociate, break apart the aqueous strong electrolytes. I put that in bold because that is key. We can then identify and cancel the spectator ions and determine the net ionic equation. So in this example, I see that it's balanced, so I'm going to dissociate the aqueous strong electrolytes. Hydrochloric acid is a strong electrolyte, so let's dissociate those into the parts, into the ions. Sodium hydroxide, aqueous strong electrolyte, we'll dissociate that. Turn into the products. Water is a non-electrolyte, so we'll write it intact, and then we have another aqueous strong electrolyte with the sodium chloride that we could write dissociated, broken apart. If we then cancel the components, the species that we have on both sides, we see that sodium ions were on both sides, that's a spectator ion. Chloride was on both sides, that's a spectator ion. So the net ionic equation that we're left with is shown here. And we've identified the spectator ions as well. The E-text discusses an acid-base neutralization involving magnesium hydroxide, solid, and hydrochloric acid. Here it's shown in a figure. Let's work through this one. What's the acid in the reaction? What's the base? What are the products? Can we get a balanced equation? And then finally, a net ionic equation. So in this one, hydrochloric acid is the acid, and magnesium hydroxide is the base. The products for the reaction will once again be water, and the ions that are remaining will form the salt. If we balance it, we see that we need a coefficient of 2 HCl for every 1 magnesium hydroxide. Being able to balance an acid-base reaction, really important skill later in chapter 4 when we do some quantitative stoichiometry calculations involving solutions. The plan to come up with the net ionic equation, same as what we just did. So we have a balanced equation. Let's break apart the aqueous strong electrolytes. Magnesium hydroxide as an ionic compound, I like classifying it as a strong electrolyte. However, notice it's not aqueous, it's solid. So we're going to keep that written together. Hydrochloric acid, strong electrolyte. Let's break that apart. The water remains intact. The salt, magnesium chloride, is an aqueous strong electrolyte. So let's dissociate that. Now we'll see what we cancel. I see that I have chloride both as a reactant as a product. So I will cancel that out because that is a spectator ion, and I'm left with all of the other reactants and products listed there. That's what the E-text is showing, where we have magnesium hydroxide solid, it's reacting with hydrochloric acid. Notice afterwards the chloride ions that are shown as green spheres, they exist both before and after the reaction. They were the spectator ion. One last one to consider, acid-base neutralization between HF and sodium hydroxide. What's the acid? What's the base? And is it a strong, weak, or non-electrolyte? HF, hydrofluoric acid, That is a weak acid and therefore a weak electrolyte. We need to be careful classifying HF because we have several other acids in the same column, HCl, HBr, HI, that are all strong acids and strong electrolytes. HF is one that we need to attend to because it is a weak acid and a weak electrolyte. The base is sodium hydroxide. I see an ionic compound that's a strong base and a strong electrolyte. If we're predicting then the products, we're going to start with the acid and the base. Once again, we're going to form water and the resulting salt, which are the remaining cations and anions, in this case the sodium fluoride. The plan to get the net ionic equation, same plan. I see a balanced equation. Let's break apart the aqueous strong electrolytes. HF is aqueous, but we just said it's a weak electrolyte, so we're going to write it intact. We break apart the sodium hydroxide. We keep the water intact. We break apart the sodium fluoride. What we cancel in this case would be the sodium, that's our spectator ion, and we have the resulting net ionic equation. When it comes to a net ionic equation, we don't need to start with this. The process that is outlined here, it will always work for us if we need to generate it. The other type of reaction that we're going to explore are these oxidation-reduction reactions. Specific skills involved with this. We need to be able to determine the oxidation number, identify what is being oxidized and what is reduced in the reaction, write a balanced reaction, and then use the activity series to predict whether the oxidation-reduction reaction would occur. This term oxidation reduction, a lot of times you see this mnemonic oil rig to describe that, where oxidation is losing electrons and reduction is gaining. Within an oxidation-reduction reaction, electrons are being transferred from one reactant to another. If we look at this figure from the e-text, it says it is the oxidation of calcium metal. And if we look more closely at the figure, the calcium metal is losing the electrons to go to the gas, to the oxygen gas. The losing the electrons, oxidation is losing. The calcium was being oxidized. One of the reactants will be oxidized, the other reduced. So in this case, the species that's being reduced is the oxygen gas. The first step in this process is we need to assign oxidation numbers. They're a form of bookkeeping, a way to keep track of the electrons that are being gained or lost during the oxidation-reduction reaction. To assign the oxidation numbers, we have a few rules, some guidelines to follow. So the first one here, when it says write the rules in your own words, this is how I think about them. So the first says for an atom in its elemental form, the oxidation number is always 0. So when the atom is all by itself, those atoms are going to have an oxidation number of 0. It could be helium, that's just listed helium, iron. Our diatomics, those are oxygens all by themselves. So in a diatomic molecule, the oxidation number is 0. And similarly, in a few unusual cases, sulfur 8 would be an example. That's another example of the elemental form. I see sulfur all by itself, oxidation number of 0. Rule number 2, this one's pretty easy. We're looking for monatomic ions. The oxidation number equals the charge, the ionic charge. This is what we've been doing when we've been constructing ionic compounds and looking at the periodic table. So if I see sodium chloride, the sodium is +1, the chloride's -1, and those are their oxidation numbers. +1 for the sodium, -1 for the chloride. How about in Na2O, this sodium oxide? The oxygen is 2-, so each of the sodiums is +1. I'm emphasizing each because when we think about oxidation numbers, they're for the atoms themselves. I needed 2 sodiums in order to get to the +2 charge, but each of the sodium atoms had a charge of +1, and that's its oxidation number. Rules 3 and 4 get a little bit more complex. Rule 3, I would say, has the most variability. If we dive into this one, we see that when we have nonmetals, they will usually have a negative oxidation number. Oxygen is going to almost always be -2. That's frequently a good starting point. hydrogen +1 when it's bonded to other nonmetals. Fluorine is always -1 in all compounds. That's great. We can always use that part. And halogens, usually -1. I see the language about usually within here. To help solve with that, we can apply step 4. So rule number 4, the sum of the oxidation numbers is going, for a neutral compound, is going to be 0. And in fact, if it is a compound that carries a charge, we can still look at the sum of the oxidation numbers. If you add up all of the oxidation numbers for all the atoms, it's going to equal the overall charge. And that's going to be useful in our problem solving. Here's some problems from the e-text that allow us to illustrate these. I find that the illustration is more helpful than just reading the rules. So if we have our different rules listed here, when do they apply? I see one example of an element in its elemental form. Sulfur all by itself, that means the sulfur atom gets an oxidation number of 0. How about rule 2 with the monatomic ions? Oftentimes that gets combined with rule 4, where we're looking at the overall charge being consistent with the oxidation numbers. If I look at the sodium hydride, sodium's in my +1 column, so that must be making the hydrogen have a -1. If I look here at the tin bromide, bromine as a -1 cation, based on its column here, gives me a -1, and since I have 4 of them, the tin must be +4. Notice in that case, I didn't memorize the tin value. I used rule 4 to say, what did I know? And now let's find out for the part that I didn't know. Same thing applies here. I see chromium and I see oxygen. I see that there are 7 oxygen atoms. Oxygen is almost always going to be -2. 7 times 2 gives me an overall charge of -14, coming from the oxygen. For the polyatomic itself, it's a 2-. So therefore, the 2 chromiums, they must add up and give me a total charge of +12. If each of them is +6, that reaches the +12. So I'm doing this back and forth, starting with what I was most certain of, which was oxygen, that would be -2, and applying then rules 2 and 4. For examples A at the top on both sides, here I see molecules with nonmetals. So in this case, sulfur -2, each hydrogen +1. In this example right here, P2O5, I'm starting with oxygen as being -2. I have 5 of those, so the phosphorus must be +5. I haven't memorized phosphorus as being +5. I've done the problem solving by starting with the oxygen. The variability of the oxidation number is illustrated here. Here are 3 examples involving sulfur. To solve the first one, if we said that the halogens are almost always -1, I would have 2 for the chlorides, each of them -1, so the sulfur must be +2. In the second example, sodium being +1, and I have 2 of those, oxygen -2, I have 3 of those. I'm starting with what I know for sure, and the last one I solve for would be the sulfur is +4. Finally, if I see sulfate there at the bottom, start with oxygen being -2. I have 4 of those, so the sulfur in this case must be +6. So this set really illustrates how the oxidation number for sulfur, it depends on what it's paired with in the compound. The last one, a little bit tricky here, is involving barium and oxygen. Now, based on its placement on the periodic table, we would say barium is going to be +2. I like that plan. This is an example where oxygen is not 2-. This is going to be a relatively rare occurrence for us. But if barium's +2, each of the oxygens could be -1. This illustrates this point right here. The major exception for oxygen is when it's in what's called a peroxide, where it is this oxygen 2 anion. We won't encounter that very frequently, but that's what this is illustrating. Calcium metal can be oxidized by nickel nitrate, similar to the reaction shown below. And it wants us to write a balanced equation for the reaction and get to the net ionic. So instead of writing it with iron, let's write it with calcium. If we are now going to take this, we want to begin with a balanced equation. That looks to be balanced to me. We're going to dissociate, break apart the aqueous strong electrolytes. Calcium solid remains, nickel nitrate, aqueous strong electrolyte, calcium nitrate, aqueous strong electrolyte, nickel solid remains. If we end up canceling, the nitrate is a spectator ion on each side, and this is the resulting net ionic equation. If I were to assign oxidation numbers, I have calcium in its elemental form having a value of 0, nickel in its elemental form with a value of 0, nickel 2+, calcium 2+, those have the oxidation number that matches their charge. So we see that the oxidation numbers changed. Nickel went from being +2 to 0. It was being reduced. We added electrons, 2 electrons in this case, to go from an oxidation number of +2 to 0. If one of the reactants is reduced, we have to have another one be oxidized, losing electrons. Calcium went from an oxidation number of 0 to an oxidation number of +2, the loss of 2 electrons. So we've just said that calcium is oxidized by this nickel 2+. If we were to consider the reverse reaction, it does not take place. When we're thinking about our oxidation reduction reactions, they will take place in one direction, and then the opposite will not take place. So how do we know what direction it takes place in? That's what this table right here can tell us. This is called the activity series of metals in aqueous solution. This will tell us if a particular redox reaction takes place. The metals that are higher on this table are more easily oxidized. That's what the arrow is telling us. Species at the top of the table are easily oxidized. Notice each of these are written where we're starting with a solid. It's giving us the ion plus electrons. It's losing electrons. Oxidation is losing. A metal at the top of the table as a solid can be oxidized by an ion that's lower on the table. So the relative placement is going to be important. To look at what we just said took place, I see calcium solid above nickel ion on the table. Excellent. This tells me that the calcium can be oxidized as the nickel is reduced. Calcium solid is oxidized to form the ion as the nickel is being reduced. I'm looking for the solid above the ion on the table for the reaction to take place. So let's apply this. Identify the oxidation reduction reaction involving silver nitrate. So I'm first going to find the silver on my activity series. The nitrates are all soluble, so this is just another way of putting silver ions in the beaker. We're thinking about, would there be an oxidation reduction reaction between the silver and platinum solid, silver ions and copper solid, silver ions and nickel ions? In order to determine that, I'm looking for the example of the metal being above the ion. And in this case, the only example I see for that involves the copper. If it's mixed with the platinum, no reaction. If the silver ions are mixed with other nickel ions, no reaction. They don't meet the criteria that I'm looking for. The silver ions will react, however, with the copper solid. The copper solid will be oxidized to give me copper 2+, as the ions of the silver are reduced to give me silver solid. Both will take place. So I write here that the products are going to be silver solid and copper nitrate. And this would then be the balanced equation. So in today's class, we're going to work on those skills. We're going to look more closely at neutralization reactions. We want to write balanced chemical equations for those and get to the net ionic. And then for the oxidation reduction, all 3 of those skills of being able to write the oxidation number, apply terms like reduced and oxidized, and apply the activity series are going to be things that we work on.